I was there late though, so that's probably why I didn't see you.
Well, the girl I was talking to was having a party there.
No, where's the baby?
Grace?
I was like,
Great. We're still happily married.
that's the way to be.
We have a.
Okay, so today what we're going to talk about is wrapping up conjugation and then looking at a special set of conjugated molecules, aromatic molecules, in which the conjugated system is now in a ring. So we'll visually look at them, how they're drawn, and then we'll look at what is the rule of determining if something is aromatic. So we look at a structure, we apply a couple questions to it, and if they're all yes, then it's aromatic. We'll look at different types of aromatic compounds. And on next Monday, we'll talk about the reactions of aromatic compounds. And so we'll start off today with terpenes. So Ruzicka won the Chemistry Nobel Prize in 1939 for formulating the biogenetic isoprene rule. So isoprene is this 5-carbon diene shown. So it's 2-methyl-1,3-butadiene. And it states that terpenes are polymers. So any polymer majors in the crowd, a couple polymer majors. So isoprene is a monomer. And when it starts bonding to itself, it makes these polymers. So in polymer chemistry, synthetic polymer chemistry, the monomers will look a lot different. But this is a monomer that nature uses, basically to form carbon frameworks. And so again, isoprene is 2-methyl-1,3-butadiene, and the biogenetic rule states that they come together in this head-to-tail manner. So you have 5 carbons, 5 plus 5 is 10, and then that gets down to these classes here of terpenes. So a monoterpene has 2 isoprene units, so it has 10 total carbons. Does anyone know what the prefix sesqui means? So it sort of means just like 1.5. So a sesquiterpene is 1.5. So that gets you 3 isoprene units for 15 total carbons. And so what happens really in plants is that this isoprene or isoprene equivalent will polymerize, and then these enzymes come in and cyclize it, and you get these structures, and we'll show some of those on the next couple slides. So we have mono, sesqui, di. This next one, sester, that means 2.5, and then tri. So a lot of terpenes are either just CH, carbon hydrogen only, or if some other enzyme has come in and oxidized it, then you'll get oxygen in the scaffold. Just so I can say I did it, I'll conceptually show you how isoprene polymerizes, and I'll check the box saying that I talked about polymer chemistry this semester. So imagine another monomer of isoprene coming along. There are 3 basic reactivities of monomers in polymer chemistry. So anionic, cationic, and radical. I'll just show you one. Those are the initiation. So you have these starting materials, you throw in something else that initiates the polymerization and causes these monomers to react with one another. And polymer chemistry nowadays is all about having well-defined polymers, which can create materials that have specific substances, or I mean specific properties. So for example, if you want to make a new paint to spray on an airplane or a boat, to make ice not stick to the plane or on the side of a boat so it doesn't get barnacles and whatnot, those are typically polymer-based compounds. So in, let's just say a cationic, if we were to treat, maybe I want to redraw this here, isoprene with an acid, so H+, that specific pi bond would react because that would form a tertiary carbocation. So you would do an H, you'd get a tertiary carbocation. And we know that this can have a resonance form because it's allylic. So now that tertiary, don't want to do that. Tertiary carbocation can be thought of as a primary carbocation. And then your second equivalent of the monomer is now supplying the electrons. So you end up with that tertiary carbocation. And so that can go on and add another one, or other things can happen. So in plants, in your body, every chemical reaction is carried out by an enzyme. An enzyme is basically a large protein, and a protein is a polymer of amino acids. And we'll talk a little bit about the structure of those when we talk about amines later on this semester. But that would be an example of a cationic polymerization. And like I said, that thing can either terminate and stop where it is or go on to do other things. One thing you might notice, the presence of that double bond. Double bonds can get reduced, again, by enzymes. There's these things called reducing agents, so NADPH, I think, that will supply hydrogen to reduce a double bond. And so that's how you can go from saturated, unsaturated to saturated. So again, just the word terpene means hydrocarbon. That's C plus H only. The oxygens get in there through other enzymes or plunking them down in there. Because it's really only CC and CH bonds, these are generally non-polar. And because they're non-polar, they're volatile, and what that means is you can smell it. You'll notice that two of these have oxygen. Again, that comes from another enzyme, plugs it in. And there's this word, you've heard of like essential oils if you're into aromatherapy or whatever. So these come from plants. So the plants make these. And you might have done this last semester. You take like a lemon and like, did you do that? Take like lemon juice or, okay. So if you take a lemon or an orange and like in your kitchen, you might have this thing with a bunch of holes in it and you like scrape it like to zest it. Like when you do that, you can immediately smell either lemon or orange. And this is what you're smelling. So limonene is the oil of lemon. Beta-pinene, that's the oil of turpentine. No shit, people used to drink turpentine during the Prohibition when alcohol was forbidden. And you can imagine that ingesting something like that is not good for you because your body doesn't know what to do with it. So it starts oxidizing it to other things. And those can be toxic. Geraniol, is the oil of roses. Not now, but maybe back in March or April when the rose garden is blooming. Those roses tend to be knockout, if you've heard that term, like a knockout rose. And so do you know what that means? So they're editing the gene sequence of that rose so it doesn't produce a smell. The smell is what attracts the bees to pollinate it. But if you don't want swarms of bees, you have knockout flowers, and it just reduces the smell. It still looks the same, still has the same color. And menthol is the oil of peppermint. So let's just look at these, and we'll just do a question, even though it's not posed on here. But how many carbons does limonene have? How many? So 10? So it's a C10, and then we would classify that as a monoterpene. And remember that they're all coming from those 5 carbons isoprene. Can you sort of see how that maps on there? There's 2 of those on there. And really, the way that I think about it is I use this, I'll draw it in blue. That methyl group is sort of the waypoint or the marker to help identify where those 5 carbons are. And I'll highlight them in red. So that's 1. Then this next one I'll do in blue. So you can see that 2 of those isoprenes have come together, and then it sort of stops. There's not a 3rd one, but then it's cyclized back onto itself. So there's no heteroatoms. There's nothing in there that gives it polarity. So it's a nonpolar molecule. The attractions between the molecules aren't great, so it's volatile and you can smell it. And so that's how essentially the modern fragrance industry works is, they're isolating things from plants. They put them in little jars. You can go to places to make your own perfumes or colognes where you take these little drippers and you make your own solution, typically in ethanol. I don't know too much about it, but like the word parfum, have you seen that on your? That means something special. It's like a certain quality. So there's different tiers of quality between colognes and perfumes and whatnot. Let's do geraniol. We'll highlight the 5 there. This might be a little easier to spot just because it's not cyclized. So there's one of them. There's the other one. And then I'll highlight in green, that would be the bond that's formed between the 2 isoprene units. So smell, your sense of smell is relates to your olfactory sense. And smell and taste are interesting because like when I see like the red in this Gatorade, it's just the light, as we said, bouncing off that molecule, and I see that wavelength. But with taste and smell, those are actually entering your body. With smell, it's hitting like a little receptor. And I mean, all of these are sort of the same molecular weight. Molecular formulas change a little bit, but the weight's the same. What gives them different smells is how they sit in those smell receptors. And so just changing the shape a little bit will change the smell. And so again, that relates back to hybridization, which gives it shape, You know, is it tetrahedral, trigonal planar, or flat? Does it have these oxygens in there? Does that help with hydrogen bonding and that sort of thing? So there's a menthol, and when I first made this slide maybe 2 years ago, the FDA was going to ban flavorings in cigarettes because that leads to younger people wanting to start smoking. So menthol has a cooling sensation to it, like minty. And so it's added to tobacco, and it makes apparently smoking these cigarettes more enjoyable. So the FDA was going to ban it. I don't know if the lobbying union won out, and they're not, but I haven't heard too much more about it. But there is menthol, and we kind of already did this, but I'll highlight the 5 carbon units. So there are the 2 isoprene units. Isoprene monomers. And remember that 2 gives us the monoterpene. So the oil of ginger is called zingiberine. Zingiberine? I think I'm saying that right. How many, can you identify the isoprene units and then count them, and then how would you then classify this terpene? So the other thing you could do is count the total number of carbons. That will sort of help you classify it as well. How many isoprene units do you see? 3. So 3 times 5, that's the 15. So that's 1.5. That gets us our sesqui. And I see these 2 methyl groups, so I'll start there in identifying them. It's 4, it's 1, 2, 3, 4, 5. And we start over here. And we'll go down this way, 1, 2, 3, 4, 5. And then the last in blue here, that's the last 5. So there's our 3 isoprene units. And just as a review, so these bonds that are just like lines, again, those reside in the plane of the screen. This dashed line means it's projected away from you. The bolded wedge means it's coming towards you. When we look at this carbon here, there's a hydrogen that's not shown. So overall, that carbon has 4 different substituents. You have a methyl group, a hydrogen, this whole ring thing, and then this chain. So that ends up being a stereogenic carbon. And remember, that means 4 different substituents. And we learned about these CIP rules where we could designate that RRS. So that's another thing to remember from Organic 1 to be able to do. So that's a stereogenic center, and right next door is a stereogenic center as well. So if we have 2 stereo centers, how many total stereoisomers can we have? So 4, so the rule was 2 to the n, so we have 2 to the 2, that equals 4. So just conceptually, so we refresh our memory on this. Say one of those was SS. What designation would the enantiomer have? R. So those would be enantiomers. And then what would be a diastereomer of SS? So SR. So those would be diastereomers. What would the enantiomer of SR be? RS. So we have 2 sets of enantiomers. And then any other relationship is diastereomeric. Again, that means enantiomers, for every S, it has to flip to R. Every R has to flip to S. But for diastereomers, at least one of the designations has to change. So SS is a diastereomer to SR. And again, that's represented by, structurally, these wedges and dashes would then have to change. So here's lycopene, which we saw when we were talking about conjugation and why food, fruits, and vegetables are colored. How many isoprene monomers are in lycopene? So one thing you can do is, like I said, those methyl groups, if you just look at the top, you can see on the left, there's like 4 methyl groups. That's sort of your waypoint or your marker on the trail. Then on the bottom, there's 4 as well. So if you're having trouble seeing all 5 at once, color them in blue. So 1, 2, 3, 4, 5, 6, 7, 8. And then with your highlighter, you can go in and identify those 5 carbons for each. Here's another terpene called squalene. And so this actually exists in your body. It's used as a precursor to make cholesterol. So, you know, if you watch the news or you read newspapers, they say cholesterol is bad for you, you shouldn't eat it. I mean, there's cholesterol in your food, but your body also produces it to a natural amount. And what it does is these steroids actually sit in your cell membranes. So a cell membrane is a lipid bilayer. So hopefully that's familiar to you from general biology. So that separates the aqueous environment from the internal environment of the cell. And these steroids sit in there, and as they're needed, they're just sort of released, either out or in. And we mentioned last semester, so cholesterol is a steroid. You don't get roid rage or jacked in the gym from cholesterol. Other types of steroids will do that, but a steroid in general is something that initiates a biological process. So it's a hormone. A hormone is a chemical trigger for something to happen. So what class of terpene is squalene? So we have the 6. So we identify, we'll pick up those methyl groups. There's 3, 4, 5, and 6. So squalene, I would say, is acyclic. It's just a chain. You have these enzymes in your body. I think there's like 35 or so enzymes that will take this and convert it into cholesterol. So each enzyme is doing one specific thing. So steroids themselves they fall under this class of compounds called lipids. Lipids are typically fatty, and that means it's CC and CH bonds. There's not a whole lot of polarity to it. And they're isolated from plant and animal tissues. So again, a hormone signals something to start or stop in a biological process. The common steroid nucleus is tetracyclic. So there's the A, I want to do that. The A ring, the B ring, the C, and the D ring. So a typical steroid will have that, and then off of those positions are other functional groups. So methyl groups, alcohols, so OH groups, or ketones, carbonyl groups. And if you take that flat structure, if you convert it into like chairs, really what you'll find is that the A and B rings can either have this bridge junction here. That would be trans, or in the other case, cis. And we're looking at the methyl to hydrogen relationship. And really the point of this is you can see when it goes to cis, that A ring is now a chair pointing down. So it's giving that molecule a different shape. In a lot of what sort of drug interactions, the reason they interact is based on the shape. If you go on to take biochem or medicinal chemistry or pharmacology, toxicology, Fisher originally came up with this proposal of like a lock and key mechanism for how enzymes react. So you have the enzyme is sort of a lock, the molecule is a key that fits in there a specific way. So the shape is what allows the molecule to go in there and do its thing, or if it doesn't fit, it can't get into that receptor. We talked about an organic 1 conformational analysis. So this cis and trans thing with the steroids, that was recognized by a Nobel Prize to Barton and Hossel for really figuring out that, you know, a 6-membered ring can have axial. So for example, this methyl group is axial, this hydrogen's axial. Or in the cis, you now have this hydrogen here, which is equatorial. So, you know, even though this is common knowledge now, it's in every textbook, at some point in time it was not. And they're the people that really sort of coalesced all these ideas and published on it to say that all of those hydrogens in that ring are actually different. So there is cholesterol, as you can see from the steroid nucleus to cholesterol. There's been some modifications of the carbon backbone at position 3 here. We now have a secondary alcohol. You see the stereochemistry along the backbone here. And then at position 17, you have this chain coming off. And you can sort of see the isoprene at the end of the chain, those 2 carbon atoms. How eventually squalene, being acyclic, goes through these transformations and folds up into this steroid nucleus. And it's actually, you know, pretty interesting. just to go onto the Nobel Prize website and look up who's won and what they won these prizes for. So in 1964, Bloch and Leinen won in medicine for discoveries concerning mechanism and regulation of cholesterol and fatty acid metabolism. So when we get to Module 3 or 4 this semester, we'll talk about how nature makes carbon-carbon bonds. And most everything that nature makes has an even number of carbons. And so why is that? So there's this thing called acetyl coenzyme A. You might have heard that in biology, but we'll show you the structure, and it's just a reagent that nature uses to provide 2 carbons. And so from 2 carbons, you add 2 carbons more, and eventually you get this even sort of number. So one last thing here, it says cholesterol is a precursor for other hormones, so bile acid. I think bile acid, like if you eat something that disagrees with you and you have a nasty burp and you get like a little burning, that's like the bile acid coming up into your throat. And then vitamin D. So I think this is the last slide for conjugation. Yes. So again, we were talking about polyenes, and then if you have them next door to each other, that's conjugated. Now the next term related to that is called aromaticity. So this has a special meaning. It includes conjugation, but now we're going to take it a step further. And the molecule that we're going to look at is called benzene. So benzene has a molecular formula of C6H6. So 4 degrees of unsaturation. Now the way I want to explain what aromaticity is, we're going to have a triene, so 6 carbon atoms with 3 double bonds. We're going to tie it into a ring. To a first approximation, we could say this molecule shown as cyclohexane-1,3,5 triene. If we're just looking at it as it's drawn, we have alternating sigma and pi bonds. We know that a sigma bond is longer than a pi bond. So anytime there's a sigma bond, it should be a little bit longer, which really wouldn't make the structure as it's drawn correct because it would sort of be misshapen. It wouldn't be as symmetric. So the issue is cyclohexane-1,3,5 triene as a conjugated system by itself doesn't exist. Not in sort of the theoretical sense. There's something special about it that makes it benzene. And so this next fact here, it says all the bond lengths are the same and equal to 1.39 angstroms. In the relationship between these two structures, there's our resonance arrow. And it's sort of subtle, but each of these pi bonds is migrating. And remember that a resonance form isn't just that and that separate. It's both things at once. So even though we have to draw it sort of as one form, each carbon-carbon bond is somewhere between a double bond and a single bond, and all the bond lengths are the same. So how do we know that this molecule is special, it's different? And we're going to use the heat of hydrogenation experiment to explain why. So heat of hydrogenation. If we start with cyclohexene, that just has one pi bond. If we do an addition reaction to that, so we're going to take hydrogen gas, palladium metal absorbed on charcoal, in methanol, and we just add H2 to that, we get cyclohexane. And then we can measure the heat that's evolved, so negative 120 kilojoules per mole. So if we take that as our normal factor, negative 120, and then we add another double bond in there, so negative 120 times 2, we should measure negative 240. But notice there's a little bit of discrepancy. It's negative 232. That number is outside of experimental error, so we can't explain it that, oh, we just did these measurements different. That difference of 8 means something. That 8 less than what it should be, that's conjugation. So by putting the double bonds together, that's the stabilization due to conjugation. And if we carry that logic further, you know, in theory, negative 120 times 3 should be negative 360. But if we consider some stabilization by conjugation, that reduces it a little bit to this negative 348. So the difference between negative 360 and negative 348 would be the conjugation stabilization. However, when you actually run this experiment, the amount of heat that's reduced is this, negative 208. So that's a significant difference between what we're projecting it should be and what we observe. So that difference of plus 140 is how we're experimentally describing this word aromaticity. So not only is the system conjugated, but now that it's in a ring, it has even more stability than what we would expect. And because it's more stable, it's going to react different than how like a normal carbon-carbon double bond reacts. So with the conjugated systems, we said that they do addition. So 1, 2, or 1, 4. Meaning that things are adding to those carbons. But for aromatic compounds, these do substitution. And you can see in benzene, there's 6 hydrogens, right? So what we're going to do is substitute a hydrogen for some other functional group, meaning that the reaction only takes place on one carbon. Even though we're showing this as a pi bond, those pi bonds, each carbon atom is not getting one thing. Only one of them is going to get the atoms from the reagent. So once we're up into aromatic chemistry, we're going to do substitution reactions. So aromatic compounds do not undergo electrophilic addition, but now this new mechanism, electrophilic aromatic substitution, or EAS. So we'll learn a bunch of reagents to either put a carbon atom, a nitrogen, or an oxygen right where a hydrogen was. The mechanism of EAS, no matter what reagent you start with, the mechanism is the same for all of them. So it has a couple steps in it, which we'll probably see on Monday when we actually start talking about those things. So the reason that benzene does this is because of that aromatic stabilization. It wants to substitute a hydrogen and remain aromatic. It does not want to give up those double bonds. So we'll talk a little structurally about benzene, the orbitals, and some other aromatic hydrocarbons, and then why understanding the orbitals is important. So we see the three double bonds as drawn, and we know that to make up a double bond, each carbon atom is supplying a p orbital. So each is supplying a p orbital, each is supplying an electron. Those electrons bond, that gets you your pi bond. And due to the conjugation, those electrons are not in between just two carbon atoms. They're delocalized around the entire carbon skeleton. So rather than showing them as like depicted like that, they're sort of in a cloud above, and I'll use the blue for the phase change below. So it's almost like a sandwich where these p orbitals on top and bottom are the bread, the carbon in the middle are your fixins, as it were. So we said that benzene was C6H6. So each carbon supplies one p orbital and then an electron in that p orbital. So if they're to all come together and not form just straight alkenes, but rather these sort of clouds, the way that we describe that is using this term molecular orbitals. A molecular orbital is like an orbital that sits over many atoms of the entire molecule. And they have sort of funky shapes, which I'll show you on the next couple slides. They're just mainly for a visual thing. Don't get worried or caught up about understanding it. The shapes are derived from mathematical equations about constructive interference and destructive interference of the equations. So we have 6 isolated p orbitals that form 3 pi bonds. And so if we form 3 pi bonds, we have to form 3 anti-pi bonds. So we have 6 total orbitals. That means we have to have 6 molecular orbitals. That's the conservation of orbitals. So 3 of them will be bonding. That's where the electrons are. And then 3 of them are anti-bonding. So we call these pi and then pi star. That's what the star means, anti-bonding. So in essence, they're empty. So here on the left, those are the 6 p orbitals. Again, each carbon supplying 1 electron. You have this dotted line coming across, and it's not written there, but I'm going to write it now because it's important for later on. That line is called non-bonding. And due to the symmetry of the 3 on the bottom, the 3 on the top, there's no orbital shown on that line. But for other molecules, they can be. So the wave function, we have 1, 2, 3. For the bonding molecular orbitals, those all have electrons in them, spin-paired electrons. We cross this line to the anti-bonding. These would be better represented, I think, with these stars to show that they're anti-bonding. And notice they have no electrons residing in them. So this is the psi 1 there. That sort of best resembles how to think about it. You have this cloud on top and then the cloud below. When you go to psi 2, now you sort of cut the sandwich in half. You can think of that as a node. That area between them is a node. There's no electron density in there. And so as you go up now, psi 3 has 2 nodes. So you've now sort of cut that sandwich in half again. And so you can see that as you go up, they have different shapes, and that all falls out of the mathematics. So beyond that, if you take benzene itself, C6H6, and you start annulating or adding other benzene rings, you get to higher order aromatic compounds. And these are called PAHs, so polycyclic aromatic compounds. And on this slide, they're fused together in a line. So you're just adding them just together. It's a straight line. So naphthalene, that's present in mothballs. Does anyone have a cedar-lined closet at home where you store your fancy clothes? Probably not. So back in the day, like moths, you know, at night, like moths would go into your house and like into the closet and like eat the fibers, and you'd end up with like little holes. So what people found is if you make a mothball made of naphthalene, that smell repels them. So it's a deterrent. And has anyone ever smelled cedar wood? So cedar wood's pretty pleasant smelling. And nowadays, any type of lumber is expensive, but cedar is like really expensive. So, but what people would do is just line their closet with cedar wood, and that would sort of help deter the moths as well. But now you just go to Walmart. It's just like a little, like a gumball sized ball. It's white. Over maybe the period of a year, that the size of that ball will decrease as the naphthalene sort of becomes volatile and goes away. But that helps get rid of any bugs. Anthracene, you've added the third one. Anthracene looks like naphthalene physically. It's a white solid. It smells a little different. These higher order ones, they just, the number of rings, so tetra and then cene. I don't think I've ever seen tetracene or pentacene, hexacene, decacene. But those things exist, and I don't have a model of it, but if you imagine like a decascene, even though it's flat, if you had one person standing at one end and another at the other, you could eventually start, remember in like second grade, they would bring out like a big blanket. You'd put a ball in the middle and do that. So these molecules can start like wiggling like that, and people study that for different reasons. Then eventually, if you were to take, I'll highlight here that blue and then this green, if you got enough benzenes lined up together, you could eventually take that blue and green and bond them to each other to make a ring. And that's called, what do you think that's called? Beltacene. So it makes a belt. And then as you increase that ring size, you can start making other molecules go in and out of that ring. And so people study that for various like mechanical properties. So if you had like a straight molecule going through that, you could make that belt move along that chain. And then you could make like a light switch or something, right? So in here it's on, here it's off, by manipulating the functional groups on the chain. So the next class, they're called angular. And you can see that rather than, for the third ring, rather than adding it in a line, it now has this bent or angled property. So phenanthrene, the nomenclature gets a little weird. Benzo C-phenanthrene is 4. Tetraphene, chrysene. And these things are found to a certain extent in petroleum, but they're also found in combustion byproducts. So when you're driving your car, like nowadays the catalytic converter is meant to convert things to like water and non-polluting gases. So a lot of these things get transformed into other non-environmentally unsafe molecules. But they're also found in soot. So I imagine living in the dorm, you don't have a fireplace unless you're paying a lot of money or something. So soot is, that black residue from fire. Does anyone burn candles in your house? Burning, other than the fire aspect, burning candles in your house is like bad, because if you're a responsible homeowner or apartment dweller, if you take your air filter and look at it after burning candles, you'll see it'll get darker and darker and darker, and that's the air filter catching that soot residue. And it's bad for your air handling unit. I own a house, and trust me, you do not want to fuck up your air conditioning unit. It's very expensive. So these things are in soot. And I think this is an interesting story. It says the regulations are written in blood. So why do I have that? If you ask the question, why are there always new laws being passed? So why are child labor laws important? So here's an interesting case. We'll talk just briefly about soot wort. It's also called chimney sweeps cancer. And back in the 1800s, this was a real issue because people, lived in these houses with chimneys. The chimneys get dirty, and then they don't, exhaust the gas from the fire efficiently. And so these are just PAHs of different, linear angular structure. And so this gentleman, Percival Pott, basically sort of recognized what the issue was. And so I'll just read this quote. I mean, it relates back to organic chemistry as a fundamental impact on human health. In their early infancy, they were most frequently treated with great brutality and almost starved with cold and hunger. They are thrust up narrow and sometimes hot chimneys where they are bruised, burned, and almost suffocated. And then when they get to puberty, become peculiarly liable to noisome, painful, and fatal disease. So essentially what happens is the molecules in soot end up being carcinogenic. And particularly what happens is they get oxidized and then they become reactive. As they become reactive, the amine groups in your DNA will react with them. And so DNA is a double-stranded helix, right? And so you have this one strand here, one strand here. It's continually replicating. That's how we stay alive. So you have an enzyme that comes along, it unzips the strand and copies it this way and that way. Well, what happens with these molecules, they will link those two strands. So if the strands are linked and the enzyme comes along, it stops. It can't copy them. And that will eventually lead to cancer. And so as you add more and more of these rings, the reactivity of the molecules increases. And so it increases to a point where I ripped off this slide just to show you the reactivity. So here's a PAH found in soot. It gets oxidized by the liver. The epoxide opens. You get this sort of more polar functional group. The other double bond gets epoxidized. That opens up to this thing, and then it's trapped by a base present in DNA. So it's a DNA alkylating agent. And then another molecule on the other strand comes over here and it cross-links them. So the reason this was prevalent in male toddlers is, what happens, you're in a tight space, you start sweating. If you have this soot on you, the sweat is carrying the soot down to the scrotum. I'm going to assume everyone in here has seen a scrotum at some point in their life. It's wrinkly. So the soot gets in there, it deposits these PAHs. And from there, because they're nonpolar molecules, they pass through the skin dermis. And then they're inside, and this starts happening. So it's basically, they end up with testicular cancer at a very early age. If you get cancer at an early age, you're kind of screwed, you know what I mean? Especially back in the 17 and 1800s where, people didn't know how to cure these things. So eventually that became phased out once this physician noticed, hey, all of these male toddlers are doing this, so that is the cause. And that's how these laws come into place. So we're not going to get into anything as complex as what you see here in terms of reactions of benzene, but that's another sort of scenario in which organic chemistry has sort of changed how we live our lives. So those were hydrocarbon aromatic compounds. You can put a heteroatom into the ring, and that makes heterocycles. So again, the heteroatom is nitrogen, oxygen, sulfur. So heterocyclic aromatics. And this is group 5 here, group 6, some more group 5, but different ring sizes now. So you can have a 4-membered ring with nitrogen, that's called pyrrole. And then if we're just going down that group in the periodic table, we hit phosphorus next, so this is phosphol. And then arsenic is arsol, which is always kind of funny, it makes me laugh. Moving over to group 6, we have oxygen, so furan. Furan actually is you can isolate it from corn cobs, and that's what people used to do. Is you just take corn, you boil the hell out of it, and eventually it will extract that furan from it. So the food you eat has many different types of chemicals. Thiophene, anything with sulfur, smells. Selenium, selenophene, and this is really bad. Sulfur is a bad smell. Like, okay, I'm not going to smell it. But selenium, once you get into selenium, you remember the size increases as you go down the group. They're relatively the same molecule, right? Furan, thiophene, selenophene. But as the size of that heteroatom changes, the smell changes wildly. Selenium compounds will actually make you gag. I mean, you'll want to physically vomit. Like sulfur is like, okay, it smells bad, but I can go away. But once you smell a selenium compound and it's in you, you will want to like vomit. If you go further down to tellurium, it's like even worse. I mean, just by changing the size of that atom and how it interacts with your olfactory senses. So other heterocycles, pyridine is going to be an important one for us because we're going to use this as a reagent, a base, to abstract hydrogens with. So we've just substituted a CH in benzene for nitrogen to make pyridine. If we take naphthalene and do some substitutions, we can get quinoline or isoquinoline. So we'll get as far as we can with Huckel's rule today. And this is the sort of test questions. When you're given a structure, you ask these questions to determine is it aromatic or not. And so what does it mean to be aromatic? Again, there's back in the day before all this stuff was known, aromatic just meant it was fragrant, like the smell, like aromatics. If you're cooking, you throw in your thyme and rosemary. But the chemical description really relates to Huckel's rules here. So it says a molecule can only be aromatic if it is planar, cyclic, and this is the first sort of thing you want to test. Is there 4n plus 2 pi electrons, where generally n is, an integer starting at 1. So if you plug that in there, so 4n plus 2, so when n equals 1, that gets 6. 2 is 10. 3 is 14. So you're basically looking for the pi bonds to count those electrons. If it doesn't obey that, like right away you can toss it. It's not going to be aromatic. So it has to be a conjugated system where we know that conjugation comes from those p orbitals of alkenes right next door to each other. We know that to get a p orbital, the carbons have to be sp2 hybridized. sp2 hybridized is trigonal planar, so all of the atoms have to lie in one plane, and they have to be cyclic. So visually, there's things you can do to just test these Huckel's rules. And the last one, no separation by sp3 hybridized carbons. If you see that separating the pi bonds, you can automatically kick it out. It's not going to be aromatic. So here are those rules. When n equals 0, that gets you 2. We're not going to talk about those in this class. That's more beyond this class. But they do exist. When n equals 1, we have 6 pi electrons. That's benzene. The nitrogen or phosphorus heterocycles, pyrrole, pyridine, phosphol. oxygen or sulfur, furan or thiophene. Then you can get up to 10, 14, etc. These other things, like in here, we're not going to discuss really. So maybe a follow-up question to the 4n plus 2. What if you have a conjugated system that just has 4n pi electrons, not 4n plus 2? These are actually classified in two different ways, anti-aromatic or non-aromatic. So they might be cyclic, conjugated, all those other things, but they only have 4n electrons. So they're classified in one of these two other ways. The difference would be they don't enjoy that stability that we saw from the heat of hydrogenation experiment. They're not stabilized by aromaticity. So examples of that with 4n. So the first one is a cyclobutane derivative, so cyclobutadiene. So it's cyclic. Every carbon atom is sp2 hybridized. The double bonds are conjugated, but we count 2, 4. So 2 pi bonds, that gets us our 4 electrons. But that's not 4n plus 2. We go up cyclooctatetraene. This one has two issues basically. Again, the electron count. But also, if you made a model of this, you would see it's not planar. Essentially, those carbon atoms start to deviate out of a plane. And then the last one, I'm not even going to attempt to draw. I don't think I could draw something 12-sided. But how do you determine if you're given a structure, even if something looks like it's aromatic? There's this other learning tool to supplement Huckel's rule. It's called the Frost circle. Even though it's a circle, we're not really going to draw a circle so much. But there's a way that you need to set it up to help you count the electrons. I'll just go through and explain it, then I'll read the rules back. Whatever shape it is, the shape of the molecule, so benzene is a hexagon. You want to orient it so you only have one carbon pointing down, and then you draw the rest of the molecule. Then you're going to cut that molecule in half. So it mirrors each other. There's an issue when the number of atoms is odd, and we won't have time today, but next week we will, how the symmetry looks. But we cut it in half, and wherever there's a vertex, we put just a line to represent an orbital. So this one becomes that. Then we have these two on the same energy level, then the 3 above. So anything below that dotted line, that's the bonding molecular orbitals. This, we said, was the non-bonding line. There's nothing residing on there, but there can be. And then above that is anti-bonding. So we said there's 6 total electrons we have to account for. We start filling them in at the lowest energy first. It's just one line, so we spin pair them. We have 2 on the next line. We add 1 here, then 1 there, and then we spin pair them. We see they're all spin paired. So this is an extension of the Huckel's rule where even if something looked like it had the 4n plus 2, if you had an unpaired electron in there, then it would be anti-aromatic or non-aromatic. So the electrons not only have to be 4n plus 2, they also have to be spin paired. And the Frost circle tells you that. So is cyclobutadiene aromatic? In our last couple minutes here, we see there's 2 pi bonds. That equals 4 total electrons. So right away we can say no, because it doesn't obey 4n plus 2. But we still want to understand its properties. So it says, according to the Frost circle analysis, which of the following correctly characterizes the number of each type of molecular orbital? So that's how you would draw it. Now, if we're to apply this Frost analysis, we're just going to tilt it and put 1 carbon on the bottom. So maybe I'll draw it more sort of diamond shaped. And wherever there's a carbon, we're going to draw that line. Then we have these 2 degenerate orbitals. And now you can see, based on the symmetry, if we draw a dotted line through it in blue, now we do have orbitals residing on that non-bonded line. So bonding, non-bonding, anti-bonding. A further extension of aromaticity, everything has to be bonding. If you have electrons in non-bonding, then it's not aromatic. We have 4 electrons to account for. So we put in 1, we spin pair the next one. We have 2 more. The orbitals are degenerate, so we put in 1, then the next one has to go in the other orbital to fill it first. And we can see that you have those unpaired electrons in the non-bonding orbital, so that automatically makes it's not aromatic. So to answer this, we have 1 bonding, so that eliminates A and D. We have 2 non-bonding, so that eliminates B. And then 1 anti-bonding, so our right answer here is C. Then we've plugged those electrons in, which is the next question. There's 2 in the bonding, they're spin paired, and then 2 unpaired in the non-bonding. So that was this question, 2, 2, and 0, so this one was A. And the next case we're going to start with is cyclopentadiene, but we'll pick this up on Monday. I just want to draw the structure. So there's cyclopentadiene. Is that aromatic? So the answer right away is no, because of this carbon right there. That's an sp3 hybridized carbon. It's interrupting the conjugation, so that immediately is a no for the Huckel's rule. And we'll go through this same analysis for this compound on Monday. And most likely what I'll have to do is revise the exam 1 date so that we get through all this material. So your exam 1 probably won't be next week, but the week after. And again, you take the exams online through ZipGrade. So it won't impact you too much in terms of being in class to do it. But I'll have to estimate how many lectures we need to finish off Module 1, and I'll let you know on Monday.